Let's get a little bit more into the dynamics of the deserts. Charney put in his words in the 1970s about a potential feedback between radiative forcing and albedo and the lack of rain leading to maybe further desertification. We'll see if that really works. Turns out it's not that simple. But what does hold up is that the deserts are regions of net radiative loss. In other words, the short wave that's coming in is heating the surface, creating sensible heat, the plumes, dry convective plumes, and so on. And there is nighttime cooling because there's no humidity and there is no clouds, so the outgoing long wave can go straight out to space, and the dust has some impact on this radiation budget. But essentially you end up with these negative numbers when you look at June, July, August mean net column radiative heating over the Middle East and Western Arabian Sea and so on. So you can see that lack of moisture does make a difference in terms of radiative balance. If you look at particular times 00Z and 1200Z with local times shown here, midnight, 1:30 a.m., 3 and 4:30 a.m. Obviously, as you go east, you are ahead in time. So nighttime, there is still a loss everywhere, but during the daytime, you can see that the eastern parts of this region begin to have some net heating, whereas it's still net loss on the western side in the deep heart of the deserts. So we will look at examples of diurnal cycle and so on at these particular locations that are noted here and see how the radiative balance or columnar heating are balanced. But Charney had said basically a self-induction effect through albedo enhancement which exists when a desert has formed or is forming. This is key because it implies that if a desert is forming for whatever reason, let's say shifts in rainfall pattern or because of human activity like deforestation or grazing or whatever, then there is a potential for self-induction to enhance desertification. This played a role in trying to interpret the long extended drought over parts of Sahel and blaming people as inducing desertification and so on. Obviously, story turned out to be more complex in terms of the impact of ocean warming on the rainfall patterns, etc. Lack of rainfall results in lack of vegetation. Dry, sandy, or rocky soil has much higher albedo than soil covered by vegetation, which nobody will argue with. Hence, desert regions reflect more solar radiation to space than their surroundings, as we already saw, if all else is equal. Desert surfaces are hotter than surrounding regions and the air above them is less cloudy, dry climates. Hence deserts emit more terrestrial radiation to space. The net result is that the desert is a radiative sink of heat relative to its surroundings, which is what we said. We can think of it in terms of diabatic heating, which we will see coming from vertical motion induced by sensible heating rising from the surface, so radiative heating warming the surface and then plumes bringing up the heat, where WP is of course the motion across pressure surfaces in the so vertical velocity in the pressure coordinate HPA per second. So W times S can be the stability of the basic state can be written in terms of diabatic heating, and the temperature, reference temperature, which can be written in terms of Brunt-Vesala frequency, and Q dot, the diabatic heating, is of course without any moisture. It just depends on the pressure level and the vertical advection of the sensible heat d theta dp. So it's potential temperature, no need for latent heating, and moist static equivalent potential temperature. Okay, We can write the net radiative heating as downward at the top of the atmosphere and upward, downward at the surface and upward. So you can see the change in convention there already. So looking at radiative and surface fluxes to get into the interpreting the data, we already know that the sensible heat flux is this expression, which depends on some coefficients and wind speed and the temperature difference. It's like how fast your skin will cool if you're perspiring, and it depends on whether there is wind, right? Latent heating, we will not worry about it here, but we remember it depends on wind speed as well and the humidity difference, but that's a non-exponential function of temperature. Total heat flux at the surface is given by net radiative heating, sensible heat. I think I said this wrong in chapter 2. It is the sensible heat due to precipitation. So when rainfall falls, its temperature is different than the ocean or land, so there is a induced sensible heat that this accounts for, and of course the latent heat. Before we had written net radiative heating as solar minus long wave, right? Not very different. So let's start by looking across longitudes at the equator and along 25 north, where you obviously have subtropical deserts, and you can see the seasonality of the condensational heating and sensible heat, which is very small here, and you will see increased sensible heat in regions where there is less condensational heating. So of course monsoonal heating is a very seasonal thing, so you can see that DJF has no condensational heating. The blue line is flat down here. Those are the net radiative fluxes, and this is the total column heating, which at 25 north is dominated by the summer monsoonal heating, which we will look at in a little bit more detail. Okay, that seasonality tends to be very strong. Okay, maybe I'll leave this for the next podcast, but we will look at details of the dynamics of deserts with these continued heat budget data.